My name is Tim Heidel. I'm a fellow here at ARPA-E, and I'll be speaking this morning with Rajeev, one of our program directors. The purpose of this session and all of the sessions occurring this morning is to try and give you a sense of what is it that we look for when we evaluate new program ideas and new projects at ARPA-E. What are the essential components that we're really looking for, and how does that fit with ARPA-E's mission? So the very first thing we always start with when we're looking at new programs and new project areas is we go right back to the agency's missions. And the agency's missions are to enhance the economic and energy security of the United States and to ensure U.S. technological lead in developing and deploying advanced energy technologies. And so those two missions and the ability to impact on those two missions really is at the core of every ARPA-E program and every ARPA-E project. And specifically below that, we have three goals that we look for when we evaluate new technologies. The ability of those technologies to reduce energy imports, to reduce energy-related emissions, and to improve the energy efficiency of the United States economy. When we actually dive in and start to evaluate specific project proposals, beyond looking at the potential impact of those technologies on the ARPA-E's mission areas, we look at these four areas. First, we look for a high impact. So we look for projects that actually have a credible path to the market, a large commercial application, something that could have a really, truly substantial impact on our mission areas. We look for technologies that have the ability to truly transform industries and transform the way that we both produce, convert, and deliver energy in the United States. We want projects that are challenging with our sense of what is possible and what is not possible at any given time. We're looking for technologies that can disrupt given technology areas and put us on entirely new learning curves and leap beyond what's possible with today's technologies and those technologies that are on the immediate horizon. We're looking for projects that can bridge between science and technology. Often we're looking for projects that will accelerate a new scientific concept that's been proven in the lab and take it through a proof of concept where we can see a path to commercialization. We're looking for projects that are not researched or being funded somewhere else. We're really looking for additionality in the projects that we're funding. And we're looking for projects that are catalyzing new interest and new investment and very often are bringing in areas of expertise that perhaps have traditionally been beyond the energy sphere. Finally, we're looking for best-in-class teams that are bringing together both scientists and engineers to tackle new problems. Very often we're looking for people who may not have worked in energy before, but have a specific skill set or specific knowledge base that might actually be very valuable in this area. We're also looking for teams that are very translation-oriented. They're teams that are not just interested in working only in the lab, but are very interested in the transition that takes a new technology to actually transition out of the lab and into the marketplace. So I'm going to talk about impact, and I'm going to frame it specifically in our electric grid and our electric power management area. And then Rajeev will follow talking about specific projects and pointing out how those projects really define these four areas. So when we look at the U.S. electric grid and we're trying to look at impact, well, first, the electric grid's impact is very clear. The total asset base in the U.S. is over $1 trillion. And with such a large, complex system, even small gains, even a 1% or a 2% benefit, all of a sudden, if you actually could deploy it out widely, would be a huge gain for the American economy. And so right away, the scale gets us very interested. This is a big problem, and we're dealing with very large-scale issues. If you dive in a little bit deeper into the U.S. grid, first, we see that the grid that we have today is very brittle. It's not very flexible. We really don't have precise control over all aspects of how it operates. And what this means is that we end up with conditions during certain times of the year when many lines are congested. And when congestion happens on one particular line, it often very easily spreads to an entire region. Small local events propagate quite a bit, even beyond reliability events. And this raises both costs and can impact reliability. We also know that reliability events today cost the U.S. economy a huge amount of money. One recent LB&L estimate gave the cost of outages in the U.S. as high as $79 billion per year. So there are huge savings to be gained if you can find ways to improve reliability and make the grid less brittle and more flexible. And so we look at these statistics and we start to say, okay, how do we make the grid more flexible? How can we build in more flexibility? We also see a huge opportunity in terms of infrastructure investment. If you look at the electric power industry and the utilities industry, there was a huge increase in investment right around the baby boom era. And much of the technology that was installed then had expected lifetimes of between 40 and 50 years, and we're now starting to become towards the end of that investment cycle. And we're seeing in this plot here, you see that the tail end of the investment in the late 1970s, and you see over the last several years we've started to see an uptick in investment again, and it's very likely that's going to continue as well. This was confirmed by a recent utility survey that indicated that much of the transmission, generation, and distribution assets that we have are starting to approach the end of their useful life. And so in these plots, the green colored bars, this is 100% is on the vertical axis in terms of the asset base that we have. The green bars are equipment that are near the end of their design lifetime, while the yellow, orange, and red are actually already past their expected operating lifetime. So this means that if you look across these different areas, somewhere between 20 and 30% of our assets are already getting very close to needing replacement. And what this means is that over the next 10 or 20 years, there's going to be a need for huge investments in this area. And that infrastructure renewal process is a great opportunity to deploy new technologies and add new functionalities and new capabilities into the grid system. We're already going to be needing to make these investments. At the same time, the resource mix on the grid is changing. This plot shows you all of the state renewable portfolio standards that exist in the U.S. today. Beyond these policy mechanisms, the costs associated with wind and solar generation are also coming down. Now, if you look at the way that we have traditionally controlled the electric grid, much of our control has been affected through generation units and ramping generation units up and down. As we approach new types of generation like wind and solar, we lose some of that dispatchability. And so this makes us think, okay, we don't have the same generation mix to control anymore. The locations of these resources will be changing over time. And so we need both more flexibility, and it also leads to start to think about, well, what are other mechanisms we can use in order to actually control and effect control on the power system?
So Tim is hopefully motivated for you why ARPA-E is interested in problems related to the electricity grid. It's an area of interest. If you look back on the existing funding opportunity announcements, it's a significant area of interest for ARPA-E. We've made investments in the neighborhood of about $100 million on the electricity infrastructure. If we look forward into the open FOA, into new funding opportunities that we see, we expect that problems related to electricity grid will be an important part of that portfolio looking forward. So how do we basically start this process? What do we see as the white space once we understand this? So Tim has already painted a picture for you for what we see as the electricity grid today. If we basically look at the control engineering, we see that it's primarily scheduling of generators. That's the way we basically balance supply and demand of electricity. That's done through some sort of centralized mechanism, whether you're in a market or in a non-deregulated area. If you basically look at the algorithms that are used to basically do that scheduling in that centralized plane, they basically assume that the grid operates in a way that's essentially linear, that the wires behave like an ideal circuit, and that the optimization problems that you do to figure out what that schedule should be are convex. It means that there's a well-defined optimal that you can easily find. If we look at the infrastructure that basically that distributes that electricity primarily throughout the United States, it's a high-voltage AC mesh grid with a radial grid that basically goes out to the end. And just for a few point-to-points, the Pacific Intertie, a few specific locations, there's point-to-point HVDC. And so when we look at that as what the grid looks like today, we had a workshop in December of 2010 really looking at, what is the white space? Where does ARPA-E need to make an investment? Where's the potential for transformational change at the scale of the dollars that we have available to ourselves? And at the end of that workshop, I think there's a website for the workshop that all of you can access, the in-feed presentations and the input that we received from the community. But some of the things that were identified is that right now, we could basically move from a scheduling-based control to really being able to do dynamic control in much the way you would control other types of systems. trying to be able to do things in real time. So we already have day-ahead markets where these schedules are created, but really trying to make the grid a little bit more reactive and responsive. Being able to reconfigure, making it so that the only thing that you control within the grid is not scheduling the generators, but actually being able to reconfigure the topology of the grid itself. So being able to route power flows was identified as one area of potential transformational impact. If we look on the control side, I think one of the areas of control that were identified is, instead of being able to do centralized control, being able to break up the intelligence of the grid and make it distributed and actually still figure out a way to be able to reach an optimal schedule or an optimal control point, be able to match supply and demand without actually having to have strict coordination and communication between all the different elements. And the other part of this is network control. So network control is a new branch of control theory created in the last 5 or 6 years that really doesn't require observability. It says, what if you don't have all the information that you need about the system that you're trying to control? How far can you get in terms of being able to stabilize that system and reach an optimality? And on the transmission hardware side, they thought that the things that were identified as things that were missing here were being able to come up with ways of actually supporting this vision of being able to route the power flows out on the AC grid, make the AC grid more resilient. In addition, instead of going just to point-to-point HVDC, being able to have multi-terminal HVDC, so an HVDC infrastructure that we could also use to route power from location to location. So let me dive a little bit more deeply into a few examples and the things that really excited us about these specific programs. So again, when we were looking at the merits of each of the individual programs, these are the 4 things that we were looking at: the potential for impact, the potential for the particular technology to transform the landscape, to really be disruptive, to really being a bridge, to really the funding that we had, there was additionality. It really didn't duplicate any existing funding, and it actually provided a bridge to the market, and that the team was really had the depth to really make these ideas happen. So let me give you a couple of examples of this. So the first example I'd like to give is a team that was seated at North Carolina State University in ABB. And the picture that you're seeing here looks a little bit like the transmission lines, the distribution lines that go outside of your house, but the transformer looks a little different. And this is an artist's sketch of a solid-state transformer. It's a transformer that basically has the potential to be able to make the grid more resilient. If a tree falls on a distribution line today, when that line goes out, it basically propagates through the transformer to a larger outage that goes all the way out, that propagates into the subtransmission and then transmission grid. I think all of us have had stories in the last year of outages that have happened. A solid-state transformer has the ability to be able to arrest that fault right at that location. So it's an active control. It's an electronic device. In addition, it can basically support renewable generation. So it can support voltage and regulation like capacitor banks would, but it can do it more actively. Now, the thing that made us excited was not just the impact here, but that this team, a university member as well as ABB, a large vendor in this space, had partnered up with Cree and PowerX to really go back and say, well, what I need in order to be able to make this cost-effective and small is I need a new platform for being able to build electronics. And so they went back, partnered with Naval Research Labs, really understood the fundamental material science to be able to make very high-voltage electronic devices. Cree realized those thick epitaxial layers that you need to be able to make high-voltage transistors. And this is the world's highest voltage transistor. It's a result that they got at the end of last year. It's a transistor. It's a single device, fits in the tip of your index finger. It basically has a 140 micron thick silicon carbide epitaxy. As you can see, at 15,000 volts of applied voltage, it only has a leakage current of 600 nanoamps. And yet, when you turn this device on, it can support almost 100 amps of current without latch-up. It's an IGBT, the same kind of transistor that we're starting to build that winds up in the inverter for your Prius or your Chevy Volt. But it's actually a device that can support megawatts of power in an active area that's only 5 millimeters by 5 millimeters. So really, this is an example of a vertically integrated team. It's basically they're covering everything from the science to making a new device, realizing that material, putting that device in a package, putting that package in a circuit, and actually implementing a full system that's going to have impact on the grid. And that's what we kind of like to see. It's a way for us to basically use the convening authority of the federal government to really be able to fund an entire supply chain to really make transformation happen. The result of that is that when you actually can have a device that's this small, now instead of the device that switches at 60 hertz like you would a thyristor, it's a device that can switch at 50 kilohertz. Now, once you get to 50 kilohertz, transformers get smaller. And so this is an example of a 30 kVA transformer. It's about the size of a sheet of paper because it actually switches at high frequency. Now let me show you another example. So this is an example of a seedling project that we'd funded under the ADEPT program. So this is before Genie. Under that seedling project, we'd given a little bit of money to Georgia Tech. Georgia Tech, again, they'd had this idea on their own in terms of thinking about the benefits of being able to get more bang for the buck for the installed infrastructure that you had. Be able to route around congestion, be able to route around points of failure. And so the idea here was to be able to create a thin converter, some electronics that you could attach to a traditional transformer that would make the transformer an active device. Now, they took that initial proof of concept to show that it's possible to make a circuit that was going to be robust and resilient. It was going to be efficient enough, low cost enough, and then if and when the transistors failed, that you were going to recover the passive transformer out of this. We took that seed project and we said, okay, well, that idea looks like it works. We can see that there's really some transformational impact there. So this project turned into a full program under the Genie Award. It turned into a program where there's an IP relationship set up where this intellectual property developed into the seedling went to Varantech, a small company. Varantech partnered with Waukesha, one of the U.S.'s largest transformer manufacturers, partnered with EPRI, representing over 700 utilities all across the world, to really understand what the impact of this might be, and then basically have a partnership with Southern to not only make one of these devices, but to make 13 kV megawatt scale units, and then make an entire grid of these, to make a 5-bus system where three of these are controlled with routers, and show that you can do dynamic power flow control with a system like this. And they partnered up with Southern to be able to demonstrate this. So again, what's attractive to us is really being able to see an entire vertical team basically develop here, right? See a clear path to market that's there, like a bridge that exists, see the team is actually strong, see the impact really being fleshed out within the scope of the program, and really see this first prototype and its benefits basically illustrated to us. Now, one of the important things to realize is that when we defined the program within Genie, looking at power flow control as a result of the input from the workshop, we didn't specify a particular technology. What we specified is we wanted this kind of functionality. This is an example of what the state-of-the-art is. It's the power flow controller that's in NIPA. It's $140 to $300 a kVA. We wanted a functionality like this, but we wanted you to beat the cost here. And we said you could do anything you wanted to do. You come up with your best ideas, come up with any technology approach. In general, that's the way that ARPA-E likes to do things. We set hard metrics, but we're not prescriptive in terms of technology. So in addition to this approach that we have, that I've shown you from Varantech that resulted from an ADEPT seedling project, we have Smart Wire Grid, really looking at a completely different approach, really being able to attach these not to an existing transformer, but being able to attach them to the transmission line, make the transmission lines themselves something that you can dispatch and control to be able to direct power flows. In addition, we had another project from Oak Ridge National Labs, being able to take a transformer and control it not by virtue of being able to change the electronics, but being able to inject a DC flux to be able to tune the magnetic properties of the transformer itself. So what we're funding is basically a portfolio of approaches. We don't know which of these is really going to be transformational, but we know that if they can hit these cost targets, we know if they can get this kind of performance, that the potential for being able to change the way we deliver electricity really exists. And so we funded, this is the approach that ARPA-E uses, is a portfolio type approach. Now, along with the hardware problems, there's a software problem that is associated with routing. If you want to be able to figure out how to dispatch your topology in addition to your generation, you've basically made your problem significantly more challenging. And so this is an example of one of 10 projects that we have within the Genie portfolio really looking at algorithm development. This is algorithm specifically for being able to do topology control. Again, it's a vertically integrated team, so what attracted us to this is really, it's got Charles River Associates, a group that's basically been looking at impact assessment, algorithm development for quite a long time, partnered with two/3 leading academic institutions, Boston University looking at optimization algorithms, Tufts and Northeastern looking at algorithms for stability, probably some of the hardest algorithmic problems that are embedded in being able to schedule and control things for the grid. Polaris, which is looking at software implementation. This is actually kind of important because Polaris is a partner with Alstom. Alstom was one of the largest EMS vendors in the United States. They helped with Polaris, and they contributed to the development of Eterra, which actually runs a lot of the grid that we have today, as well as PJM interconnections. So PJM is the largest of the transmission operators. They're the guys who actually run the scheduling algorithms. And so it basically had a partnership that included all of these guys, all of these members on one team. And the bang for the buck that we got out of this is that we're hoping to be able to, by implementing topology control, showing that it's basically computationally feasible, tractable, that there's a benefit there. We're actually looking at 1 to 2 billion in generation costs would be reduced. That 1% savings in cost of energy that Tim talked about, and we're actually looking at a $300 billion utility sales. Those are the kind of numbers that we're trying to make a difference in. So the last thing I'm going to end with is really just looking at, in the teaming session, for those of you who just came out of the leadership meeting that we had just a few minutes ago, one of the things that Eric Toon said is that when we're looking at teaming, we're looking to see if we can pull the best and brightest ideas out from adjacent fields. So one of the adjacent fields that we were looking at was looking at integrated circuits. So this is some of you might know him. This is Amit Narayan. He was a professor at Berkeley, professor at Stanford. It started a couple of successful companies in the integrated circuit design space. So he started Berkeley Design Automation and Magma Technologies, and working specifically on how do we do design and automation of design for an integrated circuit. If you think about an integrated circuit, it's a power grid, right? We're moving electricity. We've got billions of nodes on something like this. And so Amit basically took his expertise in being able to build large software systems and founded a new company called AutoGrid. And what AutoGrid is looking at doing is basically being able to create a software platform to be able to run demand response, to be able to have millions of different nodes act as virtual power sources that you can dispatch as part of the normal market operations. They partnered up with Berkeley Labs, leaders in the demand response space. So Dave Watson's been looking at this problem for more than a decade. And within this, there's actually a very hard technical problem. That hard technical problem is how do you do optimization for millions of nodes? When you've got millions of customers, how do you solve that optimization problem fast enough to be able to participate in the real-time market, in the ancillary service market? And so that's a very hard mathematical problem. And so they partnered up with applied mathematicians at Columbia University to tackle that. So they basically brought together folks who've got proven expertise in building very large software systems for other applications, partnered with experts who are looking at OpenADR, and partnered with folks who are actually going to solve, who have the potential for solving that hard nut of a problem that's embedded inside here. And so what they're looking at is basically being able to create a software substrate that any utility could use for being able to implement a demand response type program. And so the goal here is to be able to provide, to do a couple of different things. Basically take all the telemetry data coming from that smart meter. For every individual user, do forecasting of that load. For those millions of users, basically figure out how to optimally set what the demand response signal should be, and do that and basically do verification that they've actually met the demand response schedule. So they understood the problem well enough that had to be solved, understood the technical challenges, and actually gave to us a plausible route to solution. So these are examples of what Genie is currently funding, and hopefully I've illustrated with those examples, how we think about impact as we're evaluating these programs. What we think about is basically the potential for transformation. What we like to see is basically the bridge to the market that the program implementation looks at, and what we look for in our teams. All right, and so with that, maybe I'll open this up to questions. Okay. Is there a Q&A slide? So, yeah.
I've got a question about how you see ARPA-E and roll out what technology, how you see ARPA-E interfacing with big picture around smart technologies, a lot of synergy there.
So I think so. I mean, with ARPA-E, so our programs are, our programs have an extent of about 2 to 3 years. So we see ourselves as basically the first funders, and then we look for follow-on funding. That follow-on funding, we hope that happens, through the investment community, private equity, but it can also happen through follow-on programs within the Office of Electricity. It could also happen through other programs within DOE, for example, through the hub. And so we see these as things that maybe seed things that might actually wind up within a hub if we look later on. Hopefully the white space that was identified, the areas of impact, were things that will influence the way that the hub basically thinks about this. So the Office of Electricity, for those of you who are participants in Genie or participated in the workshops, you know that this is an activity that we do in very close collaboration with the Office of Electricity. Pat Hoffman, Gil Bidenwald, Hank Kensington were all at the workshop. They participated in the review process. They were at the kickoff meetings. You'll expect to see them at some of the site visits as the program gets going. So it's really a very closely tied-in effort. Any other questions? Yeah?
I'm Rajeev. LA, professor and director of the Smart Grid Energy Research Center. We work with local utilities and we also work with industry as part of the center. And one of the challenges in this whole space, and I can go back also to our presentation earlier today, and also he was in LA when we met a few weeks ago, is, you want to do very high risk technology development, and then you want to also get into the commercial world. You have on the one hand utilities that are regulated by the Public Utilities Commission. The time cycle on that investment can be very long. That's one aspect of it. The other aspect is venture capitalists are looking for very quick ROI.
Yeah.
So how do you work with sort of these two entities?
So I think actually in this afternoon we're going to have a session that's specifically looking at rules of engagement for the various stakeholders in this space, whether you're looking at a PUC, utility, or an RTO, just to sort of look forward a little bit. I think a couple of things I'll tell you is that, so ARPA-E, to be able to facilitate that, we have MOUs with utilities. We have an MOU with EPRI to really be able to facilitate an engagement between our performers and other people, other finalists, folks that we see within ARPA-E coming from the high risk, sort of high reward basis, and really helping them do the translation and making the introductions. I think the important thing to realize is that, if you look at PJM, and you'll hear this from Chantal this afternoon, is that they have pilot programs. They do some early stage investments. They get things on the grid early on. A lot of utilities actually have similar types of programs. EPRI has money set aside specifically to do those early stage demonstrations. And so if you look from the perspective of a PUC, the thing that they look for, in terms of basically making a case for how to incorporate a new technology and pay for that within the rate base, they're looking for a first utility demonstration. They're looking to see that piece of hardware gets put on the grid, is carrying real power flow. It basically lasts for a certain period of time. And when they see that proof of concept for that prototype done, it makes the case a little bit easier. And you'll actually hear from the Colorado PUC this afternoon exactly how they think about these kinds of problems. In a complementary way, when we're actually talking to RTOs, and Chantal will talk about this again this afternoon, is that we asked RTOs if we basically have this brand new algorithms. We've got 10 groups looking at new algorithms for basically how to operate the grid. How do we basically get these guys into your control rooms? And so they've got a very well-defined set of stage gates that they look at. Within the workshop, one of the things that they told us is that too much of the early stage research is done using the IEEE test bus models. 118 bus models, they don't believe it. They don't believe the results that basically come out of those things. They don't know if they scale. They don't know if they're answering some of the hard computational challenges. And of course, the most important problem is that things like those IEEE test bus models are based on a grid that was 20 years old, right? They're American Electric Power from 1982, and so they don't capture the realities of the grid, the things that are motivating changes. And so one of the things that they asked for us is basically that one of their first stage gate is show me that it scales and is relevant for things like wind integration. And so we asked that everybody within Genie have to basically look at a minimum of a 10,000 bus test case system. That they basically have to prove that their algorithms are actually beneficial using historical using historical data, and that they basically have to be able to manage the wind integration studies that have already been done by those RTOs. And so that's motivated a lot of the partnerships that you see with the individual RTOs. Now, for academic groups where it's a little bit too much overhead early on for you to basically go and basically have a partnership with PJM, New England ISO, MISO, Cal ISO, one of the things that we're trying to do is we're working with FERC to be able to develop a test-based model that you can use very early on. And so FERC and PJM have actually constructed the FERC 8500. It's 8500, right? Yeah, I think it's the FERC 8500, which is it's similar to an IEEE test bus model. It's actually got loads, got generation, but it's basically a test bus model that actually captures the modern PJM grid. So that's sort of the first stage gate. The second one is basically to run in parallel with the regular operations of the RTO and show that there's actually a benefit. And then the third one is that they basically on a pilot scale, they'll actually look at implementing. Chantal will talk more about that today. We actually had at least 5 RTOs contribute to our workshop and basically help us think about how to define the metrics for the program. And essentially all the Genie projects are basically looking at that.
Rajeev's giving you great examples of Genie project-specific milestones, but we actually have a dedicated technology-to-market team that is working to develop technology-to-market milestones right alongside the technical milestones on all of ARPA-E's projects and proposals. So that's where a lot of those ideas sort of come from, is what do we need to see in order to transition these things into the market.
From Center for Advanced Power Systems. We're part of the Electric Ship Research and Development Consortium.
Yep.
O&R has invested in the last 10 years in this space for a more specific goal.
Yep.
Can you talk about how there might be overlap in the future?
So, yeah, so I mean, I can think. So there is a little bit of overlap. I think if I look at the silicon carbide devices on the hardware side, clearly we've leveraged DoD and DoD O&R investment specifically to really build on the hardware platform to really get to this performance so quickly. I think on the software management side, we've talked to Terry Erickson at O&R. It's basically thinks about the electric ship issues quite a bit. It's a good example of the microgrid in some sense, right? You've got it when you're at harbor, and so I think there are technologies there. I think if I look at the white space, certainly the existing Genie programs don't cover all of that white space. There are a couple of areas that we could look at that are clearly missing. Dynamic control being one of them. I think that out of all the projects, there's one that basically has half of it basically focused on dynamic control. So I think there's a lot that we can basically leverage out of that. I think there's the potential looking forward. Whether it's in another FOA, some funding opportunity, something that basically looks at the grid to really kind of fill the rest of that white space in. And I think there are other programs that I think you'll hear Ash Carter talk a little bit about the MOU that exists between the Department of Defense and the Department of Energy, and ARPA-E specifically, to really look at opportunities to be able to leverage that more formally. And so you'll see an example of that later on. So actually, there's a question back there. I'm sure Tim and I will have different perspectives on this. Maybe, Tim, you want to start?
Sure. I haven't looked at the numbers in that much detail, but I would say that today that case may be weak. But as resources are changing and as the requirements that are being asked of the grid in order to integrate brand new resources, those change, the value of these new upgrades and new technologies and new control mechanisms becomes that much higher.
And I think, you can take, I can answer with two different perspectives. So one of those perspectives is you can look, so Dick O'Neill at the beginning of 2011, so he's the chief economist at FERC, wrote a paper specifically about things like topology control, right? Looking at what's the economic benefit of basically being able to reconfigure topology on the grid. In his context, he was thinking of all of New England ISO and being able to set a few relays. That paper basically looking at limited security constraints in their optimization algorithm and their unit commitment economic dispatch algorithm. Basically, they talked about it basically net savings in the cost of energy of about 4%, which, if you're looking at the cost of energy, that's the total cost of running the New England ISO grid, basically saving by 4%, being able to implement topology control, which is entirely a congestion play only. That's huge. Numbers like 1% for all of electricity in an entire regional operating area is a gigantic number. So I think there are papers out there, and I think Dick's paper is a good place to start because he's at FERC, he's the regulator. So it's nice when the regulator is basically giving you a call to action, right? Because I think Dick has even said this publicly that if you could make that problem computationally tractable, they would mandate it. So that's one extreme. I think the other extreme is that I think everyone is basically still figuring out how to manage things like renewables integration. If we look at the RPS standards that Tim talked about, we see that as something that's basically in the future. If you look at an RTO today, we haven't found one that basically does things like dynamic reserve, right? The reserve capacity that they have to set aside for being able to make up for the fact that the wind might drop down at any instant in time, that's a fixed number. It's not something that's continually adjusted. The algorithms for being able to even do dynamic reserve look like they're not being implemented yet. So I think there's a lot on the horizon that's changing in the mix for how we do generation, And that's going to have implications for everything that we do in terms of operating the grid. So I think there are things out there that are good economic cases to make.
Hi, Zach Coleman with Smart Grid today. I think that's two quick questions, I think. One, aside from conferences like this, what are you doing to link these cross-discipline groups? And two, noting that they're this closest regulator, are you working closely with Newark on a lot of these issues as well?
So right now we haven't engaged closely with NERC at this point. I think we've had some interaction with them, but the engagement has primarily been with the RTOs, utilities, FERC, the vendors, and academics and other groups.
And several of the state PUCs as well.
That's right, and the state PUCs. So, but we have only limited engagement with NERC, and so that's actually something we should correct in the near future. In terms of really looking at how to leverage some of the changes that we're looking at, I mean it's very hard to basically do something where you're fundamentally changing the way that the market might operate without actually having the market makers at the RTOs, at FERC, basically in the room with you to basically go through that. And so that's an important part of why they were always at the workshops, at the kickoff meetings, why they're members of these teams. But we see that as part of the tech-to-market process that we're going to go forward with, that within each of those tech-to-market activities, we're asking the teams to basically convene their own workshops, to basically get their own inputs from the stakeholders. And in addition, we're going to do that as well. So we're expecting that, once these programs are all up and running within about a year, we're going to have a whole series of workshops that are really focused on people who are market makers, who understand the technology well enough to understand what might have to change within the operations of the market to really be able to leverage these advantages. And so I think, topology control being one example, but I think almost anything like real-time demand response fitting in ancillary service markets. I mean, I think you can look at almost every project and actually think about what the market implications for that might be, and how does the market have to change in order to really be able to optimally utilize that new technology. And that's basically going to be part of our T2M activities. Yeah.
Is it possible to summarize the issues in computational tractability? Is it a lack of sensors? Is it storage, network infrastructure, or mix?
So I think there's many. there are many computationally hard problems. I think so. At the hard nut of the problem is that there's an optimal power flow problem that you have to solve, and that problem is it sits under a class of problems that are called NP-hard. That basically means as you scale the number of things that you're trying to control, that problem doesn't scale in polynomial time. It becomes very difficult. And so as a result, the grid today is operated using an approximate version of the solution. So when you actually do scheduling and dispatcher generators, you typically solve a DC optimal power flow problem. You assume that everything's DC, you solve that, and then you just check that you get a consistent AC solution out of that, and then you do transients. So the fact that problem is so hard means that you end up doing an approximate solution today. It also means that anything extra that you add, anything else that you try to control on there, basically makes your problem that much harder because another thing you have to set. And so, for example, if you're trying to co-optimize the topology with the generation, your problem just got a lot bigger. If now you're actually trying to co-optimize your demand and your generation, your problem just got a lot bigger. And now you're talking about millions bigger. And the generation and renewables can be challenging because it's at the end of a distribution feeder. It's things that you don't necessarily have visibility to when you're actually operating the market. So that's sort of the hard nut of the problem. I think there's a whole host of other computational problems that are embedded in that. I don't know if, Tim, you wanted to...
Yeah, I mean, in addition to the algorithms development, I think we are looking at a lot of the computational issues, and a lot of the Genie programs have very strict technical milestones of saying, this has to solve within a certain amount of time, or because we've looking out and seeing, okay, what are the computational tools that are available to utilities and RTOs that exist out there, and what are they likely to be able to actually work into their own systems?
Yeah, so I mean, if I look at if I'm looking at the unit commitment, data head unit commitment, the dispatch problem, I still have to be able to solve quickly, right, and essentially in real time, and I have to be able to. Then there are real-time markets where I have to be able to make these optimization decisions every few minutes, and then there's the ancillary service markets, and there's the volt var regulation where I need signals that go out every 2 seconds, and so embedded inside there are NP-hard optimization problems I mean, it becomes computationally intractable. And so to the extent where some of these problems have only been solved on supercomputers, and it's just not tractable for every RTO and utility to have a supercomputer access. And so, when we basically created these benchmarks, we said, well, you can't have a 1,000,000-node cluster, because actually we've had proposals where they said we're going to solve this on a 1,000,000-node cluster, because it's just not. I mean, it's great that you have access to a computer like that, but it's not a T to M type solution. So we've done things like say, well, the largest computer, like PJM's largest computer that they do their contingency analysis on, it's a 150-node cluster. That's the biggest computer you have, and you basically have to solve the problem in 2 minutes. Okay, sorry, there's a question back there. How do you get involved? Okay, so there's a couple of different mechanisms for engagement. I think if you're looking, if you're just really looking to talk and kind of put your idea out there, it's actually possible to contact us directly, and or my team, who are actually these guys all sitting in the front row, are people that they actually tell me where to go and what time. So they're the ones who control where I am. But I think you can basically set up a time. So I mean, it's easy for us to meet in D.C. or wherever we happen to be. I mean, actually end up being in North Carolina reasonably often. So that's one mechanism. I think the other mechanisms are that whenever we have a workshop, the workshops are always posted on the website when they're about to happen. There's an email that's sent out to the ARPA-E mailing list, and so anyone can basically apply and say, well, I want to be able. I think I've got this to contribute. It's relevant to the scope of the workshop, and I want to be able to attend. So that's a mechanism that we can basically your voice can be heard right from the very beginning. The concept paper, obviously, the concept paper and application process is open. There's a draft open FOA that's out on the streets, and so that's really. It's a mechanism. It's a formal mechanism for us to basically solicit your best and brightest ideas, and it's truly an open FOA. And any idea that you have that you think has transformation potential, that's the place. That's the place to send it in. Sorry. Yep. Yeah. Are we expecting any new ones? So I guess what I'll say is that the power grid is an important part of the ARPA-E portfolio. I basically can't tell you in advance of when I tell everyone when there will be a workshop. But I think if you basically sign up for the ARPA-E mailing list, which you can do on the website, you'll basically get notification of every workshop that's basically about to be scheduled. But I mean, I think the expectation, it's a huge part of the energy landscape in the United States, and so it's an area that we expect that there'll be continued investment in.
This will remain an important area, I think, for ARPA-E. Okay. Yep.
You mentioned the use of supercomputers. So obviously, if you define the problem within the parameters that you specify, you utilize something like RTPS, as long as you haven't utilized only the power supercomputer to solve the problem.
Yeah. And there's a question back there. Yep.
Now, in the great utility race become the second, which we run into all the time, you have an extremely hard time getting anybody to put new hardware in the big project. ARPA-E going to help out at all to make it help out at all to help you use the plug this with this technology in the grid.
So I guess and hopefully maybe I glossed over this, but in the programs that we're already funding, there is all the hardware programs basically have an insertion into the grid problem. So, I mean, I basically showed you an example of our portfolio. Verintech is basically going to be building a 5-bus fully controlled routable network that's in the southern distribution grid. SmartWire Grid and Oak Ridge National Labs are both partnered with TVA to basically install their hardware on the TVA grid, show that they can basically do power flow control on those systems. So every single one of our hardware projects actually has a grid insertion associated with it. I mean, in the SolidState Transformer that I described for you from NC State and ABB, that one doesn't have a partnership. There's no utility RTO partner yet, but we're hopefully leveraging the EPRI MOU that we have to be able to find utility partners, to basically make it easier. So part of our funding is definitely going into supporting the demonstration on the utility grid, on live lines, on systems that are installed and carrying real power to basically prove that the functionality that's predicted actually happens. And that's really coming from one place. It's coming from the PUCs saying that's what they need to see. They need to see that level of risk reduction before they can basically consider incorporating paying for that hardware within the rate base. They understand the impact. They understand that there will basically be an overall savings to the consumers. But before they're willing to take that risk, like you said, they need to see it installed on the grid. And so we're paying for that in all of our hardware programs. Let me just take this question up here. Sorry. So we don't do any team construction ourselves. We don't do matchmaking in this process. The teams that I basically illustrated are teams that assembled entirely on their own and came as a unit and proposed a project. We basically said, well, if you're going to be a transformational technology, you've got to overcome a certain set of barriers, and so you probably need a utility and RTO partner, if not for getting data, for getting specifications, for helping you basically proof your technology. Okay. Yeah.
Do your stakeholders participate actively in saying, okay, if you have a successful project, we will put in the dollars necessary to scale it. And then they provide you with metrics for that type of scale.
So in terms of the stakeholders, I just want to make sure I'm understanding the question correctly. So you heard Shane Kaczynski basically say that the cost share is between 5 and 20%. So 5% is for a team that's only academic. The 20% is for a team that basically is everybody else. So that 20% cost share basically comes from companies, it comes from universities basically contributing cash, it comes from companies basically contributing, doing in-kind or cash contributions. It could be coming from any element of the team. And so it could be, if I'm looking at one of these teams, it could be coming from the small company, the large company. It could be coming from the RTO or the utility partner. In terms of, do we basically rely on whoever is providing the cost share to basically do some sort of filtering? To some extent, is that what you're asking? Because that cost share is coming from a whole bunch of different entities, right? Yeah. Yep. Yeah.
Is there a process where the board says, okay, the GIT project is very attractive, we monitor that, you're hitting your milestone, which we sort of said you have to hit.
Yeah.
And based on your milestone accomplishment, they're saying, okay, now we're going to put in the bigger number to actually adopt the technology and put it into the grid on a larger scale and have a significant impact on this $1 trillion.
Yeah, so right now, the way that's done is, we basically, we have technology milestones that we basically monitor and look to meet. We have tech-to-market milestones, which are sort of a surrogate for the kind of evaluation that a follow-on investor might make, right? That whoever that stakeholder would be in the follow-on process would make. So they're sort of a surrogate, but we try our best to basically get these technologies in front of the utilities and RTOs or whoever the vendor might be. But we don't have a process right now of saying, well, let's get all the vendors and utilities in a room and basically evaluate each of the individual projects and figure out what your milestones are. In some sense, that's a market function. That's something that's outside of what ARPA-E does right now. We're happy to make introductions, but we don't do anything else other than that. As the market basically has to operate on its own to evaluate each of the technologies, to evaluate each of the projects, and basically make decisions. There's some limited amount, there's some limited thing that we as the government really should do, I think, in this space. There's a question over there.
Yes, thank you. Just another question before here. I understand it's very helpful that
So, I understand the utility of basically being able to have a test bed that acts as a proving ground for prototypes that basically come from a whole host of other programs. I guess from our perspective, it's not clear whether it's ARPA-E, it's an optimal function for ARPA-E, or really that's basically been a better function for other parts of the Department of Energy or other parts of the federal government. I think, if I look at examples in the power electronics space, in general, we haven't funded test bedding of those technologies. What we've funded is basically develop an advanced technology. You've got a partner that basically, you've got a partnership inside there, build your first prototype. If that prototype gets tested in a car, that's great, but maybe that comes as your cost share, but we haven't funded a facility that just says, at Oak Ridge National Labs is already an existing facility funded by the Department of Energy to basically test bed a whole host of new technologies as it relates to power electronics. We're not trying to duplicate that funding. So I think I understand your point. I understand the benefit of it. I think it's just we haven't figured out exactly how to think about that in terms of our primary mission area, which is to fund disruptive technology, to fund that first prototype. And so it might be something that we do as a partnership with another part of the Department of Energy. Okay, I'm going to ask do one last question. So. Mm-hmm. So, I personally don't have a metric. I don't know.
I've seen a couple papers. I don't remember the details of them, but I think that it was something like 2/3 of residential demand is the ballpark number that I remember seeing. I'd be happy to talk to you afterwards, and we can try and dig up those papers. But it's not something that I think we've looked at in a lot of detail.
Okay. Well, actually, they're telling me I've got time for another question. So was there another question over here? Yeah, I know. So, there are similar test beds at several different. Mississippi State has a test bed for grid-related things. There's a test bed at Georgia Tech. EPRI has a test bed in Lenox, Mass. So there are a couple of different test beds. I think it's just a matter of what's ARPA-E's role in basically doing that. And I think the input's useful, and it's something that we'll consider. But it's been traditionally a difficult thing for us to think about the test bedding of these technologies versus basically making the early stage investment to de-risk the technology. Okay. All right. So with that, I think you will see Tim and I in other sessions throughout the day. I think the grid is an important part of what we're going to see over the next course of the next 3 days. I think we basically have something happening on the electricity grid almost throughout every day for the next few days that we're here at the Innovation Summit. So look forward to talking to you further. Thanks a lot for your attention.